Hi, it's time for another math easy solution, and today I'm gonna quickly end the long hiatus of not uploading videos, and this time go over Heron's formula, which is basically finding the area of a triangle using only the lengths of the three sides, so not the height or the angles in between. You don't need to know that. And I'll be going over the algebraic proof that uses Pythagorean Theorem, or the algebraic Pythagorean Theorem proof. So let's just jump right in. And also, as always, make sure to just download this extension and play videos faster speed across the entire internet. And here's just the MES update, why I haven't uploaded a video in a while. So MES update, I've not uploaded a video in a long while because I'm currently researching for my latest hashtag anti-gravity part 6 video, and here's a link to it. Go and check out my first 5 videos there. And yeah, that video may in fact be one of the most epic videos ever produced, and as well as more research was put into it than arguably ever done in the history of what we like to call quote reality. Hashtag stay tuned. And it's pretty much my PhD, or my unofficial YouTube PhD. It's gonna be one of the most epic videos you'll ever see, so stay tuned for that. Hopefully I can complete that in the coming short while. So but I am taking a break from preparing that video to instead cover this very interesting formula for determining the area of a triangle from just the lengths of the three sides, something which I have never actually determined before. It never came across my mind until recently. So let's look at Heron's formula. Okay, so Heron's formula is an ingenious formulation for the area of a triangle by just knowing the three lengths of the sides of a triangle, and without needing to know the heights or angles in between. I'm actually surprised I never encountered this formula or the need to use it until recently, when I received an email on determining area of a triangle in polar coordinates. Hashtag interesting stuff. And I looked it up, I'm like, okay, that's pretty interesting. So here are the topics to cover for this video. It's an overview of Heron's formula, algebraic proof of Heron's formula using the Pythagorean theorem, go over a quick example, and also a quick overview of Heron, or Hero of Alexandria, and his Algebraic steam engine inventions. Pretty amazing stuff. So in here, let's quickly review Wikipedia. I just moved things around just to make it in better order. So overview of Heron's formula. So let's quickly review some background on Heron's formula from Wikipedia, and always here's MES disclaimer. As mentioned many times in my earlier videos, I don't need to point which ones, so just watch any of my later videos and you'll start to pick it up. So I consider Wikipedia to be just a government-controlled Orwellian data center of only government-approved topics and narratives. Nonetheless, I use it to build some quote mainstream context for any topic I like to cover. But if you find any information contrary to the Wikipedia info I reference, please let me know, as it could open up new avenues of hashtag suppressed knowledge. And there is plenty of suppressed knowledge. So let's just jump into Heron's formula on Wikipedia. So Heron's formula in geometry. Heron's formula, sometimes called Hero's formula, named after Hero of Alexandria, gives the area of a triangle by requiring no arbitrary choice of side as base or vertex as origin, contrary to the other formulas for the area of a triangle, such as half the base times height, or half the norm of a cross product of two sides. And that's looking at vector calculus, so check that up, or linear algebra, whichever one of the two. So anyways, so this is how, just here's a triangle. Like, there's a triangle with sides A, B, and C. So if these are the sides, if this is point A, vertex A, that's alpha, and then the length of that is across there, goes to A. Same with here, B has beta, and then there's gamma for C, the third letter of the Greek alphabet, and those are the lengths. And here's a formulation. So Heron's formula states that the area of a triangle whose sides have lengths A, B, and C is A equals to square root S times S minus A times S minus B times S minus C, where S is the semi-perimeter of the triangle. That is S equals to A plus B plus C divided by 2. MES note, the semi-perimeter is just half the perimeter of a polygon, and a polygon, it's just, if you haven't graduated calculus or graduated high school, it's a polygon, just a closed loop of straight line segments. And as you can see here, the full perimeter is going to be A plus B plus C. Divide that by 2, is going to be s like that, and here s is in this formulation at each of these points, and it's often used as a semi-perimeter, just given its own variable, just because it makes calculations simplified in some cases. So Heron's formula can be also written as this. So instead of just this, you could write it in this way, like this, 1/4 square root, etc., etc. I'm just not going to read those. So let's go over a quick history there. The formula is credited to Heron, or Hero, of Alexandria, and a proof can be found in his book Metrica, written Common Era 60 or AD 60. It has been suggested that Archimedes knew the formula over 2 centuries earlier, and since Metrica is a collection of the mathematical knowledges available in the ancient world, it is possible that the formula predates the reference given in that work, and a formula equivalent to Heron's, namely this one right here, a equals 1/2 and then ac squared, etc., where a is greater than b greater than c, was discovered by the Chinese independently of the Greeks. It was published in Shuzhang mathematical treatise in 9 sections, written by Qin Zhizhao and published in 1247. And then the proofs, there's several different proofs. Heron's original proof used cyclic quadrilaterals, while other arguments appeal to trigonometry as below, or to the incenter and 1x circle of the triangle. I can go over what those are, but what I'll do is I'll go over the trigonometry, or the algebraic one, just using the Pythagorean Theorem. It's also in the Wikipedia there. And so let's just jump right in. So while there were many different methods for proving Heron's formula, or there are many different, I prefer the method that involves the Pythagorean Theorem, which I illustrate below. Yeah, and also another note is, since we know that the common formula for the area of a triangle is just base times height divided by 2, we can use the Pythagorean Theorem and a whole lot of algebra, as I'll show, to derive the height, because we know the base. And the base is just one side of the triangle, or whichever one we choose to set the height about. So let's look at this right here. So let's just draw that triangle. I'll draw it like this. If this is A, this point, or I'll just make this length is A, like that. So let's just say we have 3 sides like this. So this is A, and I'm going to call this B, and this one right here is length C. So this length C, but what I'm going to do is I'm going to draw the height of this, just anywhere. This is going to be H, like this. So this is H, and there's right angles on both sides, like that. And I'm going to call this distance right here D. So now the difference at this height right here is going to be the difference between C and D. So this is just going to be C minus D. And now what we could do here is, well, we could apply the Pythagorean Theorem, and how, because we have 2 right angle triangles over there. So recall the Pythagorean Theorem, as I've covered in my earlier videos. Put the link in the description below. So Pythagorean Theorem, like this. So for the left one, we know that, well, the hypotenuse B, so B squared equals to the sides squared. So D squared plus H squared. Yeah, so we have this one right here, but we also have it on this side here. There's another triangle there where the hypotenuse is A. So we have that, and A squared equals to, right here is going to be, I'm just going to write this as H squared there, plus C minus D squared. Yeah, so now in this easy formulation right here, we could move this over to this side and then end up getting something that looks like this. This is going to be H by itself, H squared equals to B squared minus D squared. So in other words, we have a formula for H, and we know that the area is just equal to base times height divided by 2. So we just need to, well, solve for this D right here. So we have B. B is just the length of one of the sides that we are given, and that's just over there. So we want to solve what D is. So we need to solve this. So let's write that down. Want to solve for D. Now one way we could do that is, well, we can move this over to this side. Actually, the other way around. I'm going to move this over so we have H by itself. So what we end up getting is H squared equals to, well, A squared minus this, C minus D squared. And now we could just expand this out, so we'll have A squared like this minus, and then when we expand this, and before the reason we're going to do that is we want to get this, just simplify it, and then what we'll see is that we could subtract this equation or this equation from this equation to cancel some terms out. So what we'll do is just expand this to see what happens. So c is going to be minus, and then c times c, because this is just going to be c minus d times c minus d. This is going to be c squared minus c times d, negative. It's going to be cd, d times c. This is going to be negative. It's going to be 2cd. Then d times, negative d times negative d is going to be plus d squared, like that. This equals to a squared, just take the negative out. A squared minus c squared plus 2cd minus d squared, like that. So this is equal to h squared over there. And now what we can do is, well, if we shift this over to here, line these up together, we have h squared equals to, well, we have a b squared. So I'll just write that over here, plus b squared. Nothing else lines up besides this negative d. So we have negative d squared like this, and then we have a cd. So we have two terms of d, but then we can cancel this out by just, well, subtracting. So what I could do is subtract. I'm going to put a bracket like this. Subtract, and just do a basic subtraction of formulas like this. So then h squared minus h squared is equal to 0. Equals to this one, a squared minus a squared, negative c squared minus 0, c squared. This is going to be plus 2cd, and then minus d squared. Subtract this by this. This is going to be, the whole thing's going to cancel, be positive. So then that's 0. I'll just write that as 0 plus, now this part right here is negative b squared. So we have no b squared, so 0 minus b squared is just going to be negative b squared. And now what we could do is, well, move this and this over to this side so that we have this by itself, like that. So this one's going to be by itself. So what we have is 2cd, because now we just want to solve for d, remember that? This equals to, this is going to be negative there, so we'll put a negative a squared, put this in front, so negative b squared subtracted, it's going to be positive b squared, negative c squared is going to be plus b squared. And now what we could do is, well, just divide by 2c on both sides, so we get d like this. D equals 2 negative a squared plus b squared plus c squared over 2c, like that. Yeah, so now that we have this, in fact, we just found the formula. We could just plug this inside here and then put that in the basic area equals base times height divided by 2 formula, and we're done. We want to make this just more simplified, as is the Heron's formulation. So let's just plug this inside first and then simplify. So we're going to throw that in there. I'm going to put d, circle this, put a check mark like this, and that is, so we got to this point, is just pretty much half the battle. Now it's just the fun algebra project. So now we have thus h squared, remember h squared is above here, equals b squared minus d squared, equals b squared minus d squared. Let's write this a bit neater. This equals to now b squared minus, now put this whole giant thing inside. It's going to be negative a squared plus b squared plus c squared, like that, divided by 2c, and then, yeah, just like that, and this is going to be squared. And now the algebra part in here is, we don't want to deal with the square root there, so what we could do is, well, recall the difference of squares. So recall my earlier video, put a link in the description below as well. Yes, if we recall difference of squares, and difference of squares is basically, if you look at this multiplication, b plus d times it by b minus d. In this case we're using b and d like that, just so we can line them up. If we have this, multiply this times this is b squared, and then this time, then this times here is going to be negative bd, and likewise this times this is going to be negative bd, so that's going to be a negative, actually not negative, it's going to be positive bd, so plus bd, and then over here d times negative d is going to be negative d squared. In other words, this cancels when we have a difference of squares and you're subtracting them like that. Actually, I mean, this is a difference of squares, is when you have this kind of multiplication like that. So this cancels, so we get a b squared minus d squared, like this. So in other words, this right here equals to b plus d times it by b minus d, like that. So let's just write that down right here. Thus Thus h squared equals to b squared minus d squared equals to, well, just this part, b plus d, and then b minus d. But then we have d as this part. Yes, so now we don't need to have this big giant square of the d there. So we could just have it regular like that there. So this equals to b plus, then the top's going to be negative a squared plus b squared plus c squared over 2c. So yeah, I warned you it's going to be a lot of algebra. It's pretty fun to follow along though. So now we have b minus, b minus, and then here's part negative a squared plus b squared plus c squared over 2c, all bracket like that. So now what I want to do is have the same common denominator in all of them. So what I'll do is we'll multiply this part here by, well, 2c over 2c, this 2c over 2c, so it's the same there. Now we're going to have, we could combine these all together. So this equals to 2bc, and then minus a squared plus b squared plus c squared, and then I'll put a bracket like this, and then this part right here, and also this is going to be all the same common denominator as 2c, but then we also have 2c multiplied by each other. This is going to be, well, I'll put this like this, 4c squared, because we're going to have a 2c multiplied like that, just combine them together. So this is going to be 2bc minus, this is going to be plus now, plus a squared, and then minus b squared minus c squared, like that. And now what we'll notice is, well, we have a 2bc, and then we also have a b and c. If we look at all the terms besides a, what we have is, well, this part and this part right here. So what I'll do right now is note that these two additions, so note, I'll put a line like that, so note that 2bc plus b squared, plus b squared plus c squared. Well, if we just rearrange this equals to b squared plus, just move this over to this side and this over to this side. We're going to have, this is going to be 2bc plus c squared. Now this one is just basically factoring out. This is the same thing as writing, b plus c. B plus c squared, because if we just look at the here, b times b is b squared, b times c is plus bc, and then again c times b is the same thing, so we've been added 2, and then c times c is a c squared. So we just expanded like that. So that's just this part right here. So in other words, this can be replaced with b plus c squared. Also on this side, if we look at over here, if we look at this, and now we just look at the part over here. And yeah, now only difference is we have the subtraction. I'll put an arrow like that. So I'll write also, we have 2bc minus b squared minus c squared. Again, move this over there. Move this over to the other side like this. This equals to negative b squared plus 2bc minus c squared. But in this case, I'm just going to factor out the negative, so we have a negative out of there. So now we have b squared minus 2bc plus c squared. And now this one is very, very similar to that. This is just going to be negative, well, b minus c squared. Because if you look at this, this is just going to be negative, and then expand this out, b squared, then b times negative c is going to be negative bc, negative c times b, we're going opposite way, it's just going to be the same thing, negative bc, so add those up, negative 2, and then negative c times negative c is plus c squared. So just basic expanding, it gets to that. So in other words, we can replace that whole thing with a negative there on that side. So in other words, the only thing that remains over here is this part and this part. The rest becomes, this one's on the left side plus b, over here bracket b plus c all squared, and the other one subtracted by b minus c all squared. So yes, so what we finally get is right here. Thus we have, all the way scroll up here, this is just our h squared. So we have h squared equals to, and then we have divided by 4c squared, but I'll just write this instead here. So we have b plus c all squared, and there's a bracket there, so I'm going to write a square bracket, and we have a b plus c squared minus a squared, like that. And then on this other side we're going to have an a squared minus here. I'm going to put both of them as a subtraction on the other side. So I have a positive minus a minus another positive. I mean just minus another term, not positive. So we have like that. So a squared minus this, these two are going to combine into a negative b minus c all squared. So in other words, we add that on this right side, b minus c squared, like that. And then this is going to be divided by, again, 4c squared. But now what we could do is, well, apply the difference in squares. Again, these are just a difference in squares. You have a square here, subtract by square there, a square here, subtract by square there. So apply difference in squares again to get rid of this extra square on the b plus c. Difference of squares right here. And I'll write this again, I'll make this caps lock, just because, like that. So if you look at our difference in squares here, if you have a difference in squares like that, we just have now each term plus it and minus it. Alright, so moving along, we're just going to look at this over here. So the difference in squares, we're going to have this here is going to be h squared equals 2. And I'll put a giant bracket again, because we're going to have this b plus c. I want to keep that bracket in there just for easy to understand how we did this. So we're going to have a b plus c. This is going to be now times it by, actually no, b plus c plus a, like that. Here, just move this to the left actually, like this, because we're going to have to have, if this is two square brackets on each side, we're going to have now 4 terms. So this is 1, 2, we're going to have 4 once we apply the difference of squares. So b plus c plus a, then multiplied by b plus c minus a, that's the first one. Now the second one here, we're going to have a plus b minus c, like that, and then a minus b minus c, like that. And this is all divided by 4c squared. And again, just scroll up to see that again, the difference of squares. So we have b plus d, or this one term, when you add them together and then you have to subtract them together, is equals to the difference in squares. So the subtraction of squares, like that. And now what I'll do is I'll get rid of these brackets, just simplify it. I'm going to put all the positives on the left side, all the negatives on the other side. So in this one here, we're going to have an a, just move this around, a plus b plus c, like that. And in this part here, just remove that bracket, so we have a b plus c minus a, like that. And then this part right here is going to be, well, an a plus b minus c, like that. And then here we're going to have an a, this is going to be minus b, let's put that on this side, and then minus negative c is going to be plus c, like that. And you'll see why I do it like that in a bit. So this is 4c squared. And now notice we have this a plus b plus c term over there. So what I'll do is I'm going to call this here, and I'm going to call let s equals to the half perimeter, just define it like that so it's easier in the calculation. So it's going to be a plus b plus c, which is full perimeter, divide this by 2. Alright, so now that we have this, notice what we have for each term right here. So for this a plus b plus c, that one as well, if we just move the 2 over to the other side, so we get a 2s equals to an a plus b plus c, so that this equals to 2s. And now here we have a b plus c, so what we can do, in this case, we're going to move this over to that side, so we have a 2s minus a equals to b plus c, like that. So this part right here equals to 2s minus a. And now here we have an a plus b, so instead we'll do the c, move it over, so we have a 2s minus minus c equals to a plus b, like that. So that's just a plus b equals to 2s minus c. and likewise here's a plus c. So yeah, a plus c, so we have a and c. We move the negative or the b on the other side, so we get a 2s minus b equals 2a plus c, like that. So we have a plus c, draw the better loop like that. This is going to be 2s minus b, like that. So 2s minus b is a plus c. And now we could finally simplify it further. So put an arrow all the way down. This is going to be our h squared. H squared equals 2. So h squared equals 2. Yeah, equals to over here 2s, and then we have 2s minus a, but there's an a there, 2s minus c, there's an extra c, 2s minus b, and there's an extra b there. So we have 2s, like that, is one of them, so 2s. Now we have 2s minus and minus a, like that. So we have 2s minus a, second one there. And now we have a 2s minus, what is this one, c, I think? So minus c, minus c, minus c. And then the other one is 2s minus b, like that there. All divide this by, what is it, 4c squared, 4c squared. So what we could do here is cancel the 2, this can be just 2 like that, and also we could put a 2 here, and add these up in both of these, a's, the c's and b's, and move those around. So we get like this can be s, 2s minus, I'm going to put this in front actually, 2s minus 2a, and then do this one and put it forward, 2s minus 2b, and 2s minus 2c, just put the c on the end for just order. So now we have 2c squared, and now we could do is factor out the 2, we'll factor out on all of them, so we're going to have a, this equals to, factor this out, let's put an s, times it by 2, and then s minus a. Here we're going to have, well, 2 s minus a. Now here we're going to have another 2 times 2 times s minus c, and all divided by 2c squared. So we have this cancels with this. This is going to equal to, now this is 2 times 2 is just 4 s minus a. S, yeah, whoops, made a mistake here. This is B, not A. So this is B, like that. Now we're going to have S minus B, and then here S minus C, all over C squared. And also forgot the S there, so this is going to be a 4 times S, like that. 4 times S minus A, S minus B, S minus C, all over C squared. And remember, this one is just our H squared. So that is our H squared, like that. And now what we can do is recall the formula of a triangle. This is simplified as simple as we can get this H squared. So recall area of a triangle. Area of a triangle, like this, is equal to A, which equals to, well, base times height. I was right, base times height, like that, put an extra capital B, like that, divided by 2. And in our case we chose, remember, I believe C was the base. Let's scroll all the way up. What did we choose on the derivation? So C is the base, so this equals to base, this equals to height, like that. So C is equal to base on that case. So we scroll all the way up, we have right here A equals to base, which is C, times by height, which is H, divided by 2. So this equals to C over 2 times it by, and now this one here, we're going to look at the square, or the square root of this. And remember, a square root of any square like that, you could have a plus or minus, like that. I'll put a bracket plus or minus, and then I'm just going to choose a plus because it doesn't make sense for a negative. In this case, we want a positive area, is whenever you squared like that. This is going to be square root, this whole giant thing over there. This is going to be 4s, s minus a, s minus b, s minus c, all divided by c squared. And now going even further, what we could do, so we could simplify this even further. So we're going to take the positive of this square root like that. And also this c over 2 can also be equal to, well, again, we could look at the plus or minus. We could do a plus or minus square root of a, just squaring these both. So c squared over 4 like that. And then just take the positive. So that just equals that. You could just square this, the square root this is going to be c, and divided by, c divided by 2. It's going to be this one there. But since the square root can be positive, plus or minus, because the inside is always positive like that, just by definition, just put that positive there just to always keep in mind. Otherwise, someone will email me wondering why I didn't make sure to always keep this little caveat, this plus or minus, and just choose the plus instead of assuming that it's always going to be positive. So, anyways, that's a lot of principal square root mumbo jumbo. Might go over it in later videos, but I think it is pretty interesting stuff. So, anyways, choose the positive side of that, and we're choosing the positive side of that one. Square root 4s, s minus a, s minus b, s minus c. And the reason we're doing this is because we can combine the two square roots, and when we combine them, we end up having, or actually we don't even need this bracket. So we can combine these together. This is all just square root, all the same power. So what we could do is cancel the 4, c squared cancels. And now we choose the positive. So this equals 2 plus, and this is absolutely amazing. So this can be s minus a, like that, s minus b, s minus c, like that, and absolutely amazing. Yeah, so we have that like this. So just put this better like that. So the area equals to this amazing formula, s times s minus a times s minus b times s minus c, hashtag absolutely. Yeah, it's absolutely amazing. I'm just gonna write that, absolutely amazing. Heron is my hero. Amazing. So yeah, absolutely amazing. So from all that algebra, it's like 30 minutes in this video, all this for finding out the area of a triangle just with the 3 sides. You end up getting this nice, neat little package formula. Absolutely astonishing with all that algebra work. So yes, mathematics is quite ridiculous, but quite amazing when you follow along. But anyways, so example now, let's just go over this. So example, if a triangle has lengths A equals B equals 4, B equals 13, and C equals 15, what is the area of the triangle? Well, let's just draw this triangle out. So it's going to look something like this. Well, if A is the short length, I'm just going to draw A like this. This is going to be 4. B is the medium length. I'm just going to draw this over here, 13. And here is our... like this is equal to B, this is equal to A, this equals to B, and now we have C equals to 15. It's a longer one, but that is the base, like that. But it doesn't matter which one you choose, because it's always going to be the same. So S, so first let's get S, which is the half perimeter. So S equals to A plus B plus C divided by 2, which equals 2. A is 4 plus 13 plus 15 over 2. This equals to, well, let's see what this is. 13 plus 15, that's, well, 28, because 15 plus 15 is 30 minus 2. 28 plus 4 is 32 divided by 2. This equals to 32 divided by 2 is just, well, 16. Like that. 2 goes into 3 1.5 times. 1 time, remainder is 1, so we have 12. 2 goes into 12, 6. So anyways, so we have 16 is S, like that. And now the formula for area is equal to A equals to the square root of S, S minus A, S minus B, S minus C, like that. So the square root of it, and this is going to equal to, this is going to equal to, well, 16, like that. Let's draw this a bit better. My pen's not working properly. So we're going to be 16 like that, times it by, S minus A, so 16 minus 4, and then 16 minus 13, and then put a better subtracted sign. Then 16 minus C is 15, like that. This equals to, I don't know why I'm writing so messy right now. So this is equal to, well, the square root of 16 is just going to be, well, 4, let's get that out of there right now. Then we have square root 16 minus 4 is 12. Times it by right here. 16 times 16 minus 13 is 3. And then 16 minus 15 is 1. So what we end up having is 12 times 3 is 36. So 4 times square root 36. And square root 36, that's just 6 times 6. So that's a 6. So we have 4, or we could have negative 6 times this. Let's put this in bracket. Equals to 6 like that, or plus or minus 6. I'll just take the positive. Because technically if you have any square root sign, you can have a negative 6 times negative 6. That's going to be, the negatives cancel out, becomes positive, so it's 36. Or plus 6 times plus 6, that's going to be 36. Anyways, that's very interesting stuff. I'll have to dive into that later. So this is going to be 4 times 6, which equals to 24 is the area, like that. And there we have it. Absolutely amazing stuff like that. So we calculate the area of a triangle just by knowing the sides and applying that formula. Absolutely amazing. And now if we continue that Wikipedia article on Heron's formula, basically after this example, it said, in this example the sides, lengths and areas are all integers, because notice I just had all these 4, 13, 15, making it a Heronian triangle. However, Heron's formula works equally well in cases where one or all of these numbers is not an integer. An MES note: recall that an integer is just a whole number, i.e. a number that can be written without a fraction component. For example, 21, 4, 0, and negative 2048 are integers, while 9.75, 5.5, and square root 2 are not. Etc. So if it needs a decimal or not a whole number or a fraction, then it's not an integer. So anyways, now let's look at a brief quote mainstream history lesson on or history of Hero of Alexandria. Very fascinating stuff. So Hero of Alexandria, or also known as Heron of Alexandria, from 10 AD to 70 AD, was a mathematician and engineer who was active in his native city of Alexandria, Roman Egypt. He is considered the greatest experimenter of antiquity, and his work is representative of the Hellenistic scientific tradition. Hero published a well-recognized description of a steam-powered device called an aeoliopile, sometimes called a Hero engine. Amongst his most famous inventions was a wind wheel, constituting the earliest instance of wind harnessing on land. He is said to have been a follower of the atomists. Some of his ideas were derived from the works of Subtraction. Much of Hero's original writings and designs have been lost, but some of his works were preserved in Arabic manuscripts. Here is a 17th century German depiction of Hero. Looks like some sort of Greek god. So going further, 10 AD, 70 AD, Alexandria, Roman Egypt, and he's known for the aeolipile. I'll show you a video of it. It's pretty amazing. So an aeolipile or aeoliopile, also known as Hero's engine, is a simple bladeless radial steam turbine which spins when the central water container is heated. Torque is produced by steam jets exiting the turbine, much like a tip jet or rocket engine. In the 1st century AD, Hero of Alexandria described the device in Roman Egypt, and many sources give him credit for its invention. The aeolipile Hero described is considered to be the first recorded steam engine or reaction steam turbine. The name derived from Greek word, this one, aeo, I'm not going to pronounce that, and Latin word pila translates to the ball of Aeolus, Aeolus being the Greek god of the air and wind. So here it is. When you heat it up, then you're going to have steam pushing on both sides. You're going to have a little spin around there, and you can generate some sort of rotation to get collect energy or electricity and whatnot. So that's an illustration of Hero's aeolipile, and here is a classroom model of an aeolipile. You just heat the bottom, the water or gas liquid heats up, shoots out, and then you have some sort of rotation. Let's check out this video. It's pretty amazing. So home-built aeolipile Hero steam engine running, and this guy he made himself, made from a copper water level float and copper pipe from the hardware store. Everything is soldered with bearings. Solder bearings are from an RC race car. Let's click this right here. Alright, so here's the video, and then let's turn up the volume a bit, and let's play it. Is that pretty cool? You just heat it up and it starts shooting gas out and it spins. And now you're generating some electricity if you have it connected properly. So, and let's see how fast it goes. Just the hotter it gets, the faster it goes. Anyways, absolutely fascinating stuff like that. So, going further, yeah, amazing stuff. Anyways, that is all for today. If you follow along this pretty extensive derivation video of Heron's formula, very fascinating stuff. Also the example and that brief quote mainstream narrative of him. And if you see my earlier videos, you'll know why I always say mainstream. But anyways, I won't get too much into that. Hopefully you learned about this video. This is all for today. If you follow along, like always, notes will be in the description, in the video description below. You can download them in PDF form, and also it's on Steam. And also make sure to wait for my upcoming anti-gravity part 6 video. And I'm not joking around when I'm saying it's gonna be one of the most epic videos, arguably of all time, assuming I didn't make any mistakes in the in the research, but it is pretty epic. So follow along and make sure to watch my anti-gravity free energy video series, and also just test out and play around with science experiments yourself, regardless of whatever mainstream narrative it is. In other words, if it doesn't make sense to you, find a way to make it sense to you. Anyways, it's all for today. Like always, you can download these exact notes, the link in the description below, as well as viewing these notes on Steemit. I'll be uploading those shortly after I upload this video, so it will be in article format. Anyways, that's all for today. Thanks for watching, and yeah, stay tuned for another math easy solution.